All right, everyone. So welcome to our final Monday Foundation seminar of the fall semester. I'm very happy today to welcome my previous office mate, Kevin Nguyen, who's now a postdoc at King's. We've had many discussions over the time that we shared together at BHI, and I very much look forward to his talk, which will be on the cosmological constant problem and its dynamical resolution. So the floor is yours, Kevin.
Thanks, Martin. Well, thanks for having me today. I'm very pleased to be again virtually, at least at the BHI. So today I want to talk about the cosmological constant problem and some work I have done in collaboration with Oleg Evnin and Victor Massard on a scenario by which this problem might be resolved dynamically. The talk is not intended to be very technical. After all, it's a foundation seminar, and there are people from various horizons. So I'll try to emphasize the concepts rather than the technicalities. And I would like to first start with a reminder of the origin of the cosmological constant problem from the viewpoint of QFT and the renormalization group. So, yeah, and then I'll discuss more specifically two naturalness puzzles in physics. So there is the electroweak hierarchy problem, there is the cosmological constant problem. Then I'll discuss, well, I'll present the approach that the Hubble expansion rate may be very slow, and that would like go around or bypass the cosmological constant problem. Okay, so that's basically the plan of the talk. So first, let me talk a bit about the renormalization group flow and the modern view on quantum field theory. So originally, people working on or starting working on quantum field theory encountered UV divergences. And this was, of course, an issue because if you have divergent answers to your computations, what does it mean? They found a way to read those divergences systematically, depending on whether the quantum field theory under study is either renormalizable or non-renormalizable. So if it's renormalizable, that means that you can cancel the UV divergences with a finite number of so-called counter terms. So you can add a few finite divergent pieces to your Lagrangian in order to remove divergences from the end results. If a theory is non-renormalizable, that means that you need an infinite number of divergent counterterms. And originally, it was thought that only a renormalized due to Wilson's approach on well, renormalization. And the idea is that is the in perspective the following. So we see UV divergences as an artifact of the continuum limit of quantum, which would act naturally as a UV cutoff. For example, in string theory, there is the string length. And indeed, string theory does not suffer from UV divergences, but maybe a more down-to-earth example is simply lattice QFT. So people working in lattice QCD or QFT, they know very well that they can discretize their quantum field theory on a lattice, and it makes mathematical sense. So there are no UV divergences, and if the lattice spacing is taken to be much smaller than the typical length scale probe, do not really depend on the choice of lattice spacing, if it's small enough. So the viewpoint of Wilson is the following. There is a more fundamental QFT at higher energy scales. We do not probe this more fundamental theory yet. It is associated with an intrinsic UV cutoff. Here, I chose an energy scale, MUV. And there is a way to, from this more fundamental theory, extract a QFT by, well, coarse graining. So what you do is that you, for example, you would expand your fields in Fourier modes. Those modes are which have a frequency or energy much bigger than the low energy scale mu at which you're going to do experiment. Those you simply integrate them out, and their effect on low energy physics will simply be reabsorbed in a renormalization of the coupling constant. So this process is called integration, the integration of heavy modes, but it's also simply the renormalization group flow that Wilson has introduced. If there are any questions, please interrupt me. So now we can classify the coupling constant of a theory depending on how they flow or how they change under renormalization from the more fundamental theory at the high energy scale MUV to the low energy scale mu that we're interested in. And essentially, you divide the couplings into those which increase towards low energy. So these are called relevant because they're relevant at low energy. So there is, for example, if I consider self-interacting scalar field, then those relevant operators are the vacuum energy, the mass of the scalar field, and there are coupling constant that decrease towards low energy, and those are called irrelevant. For example, phi-6 interaction of or higher power of the field, those are irrelevant. And then there is a critical case, which is called marginally relevant or irrelevant. And those are coupling constants that decrease or increase, but much slowly, much more slowly than other coupling constants. In particular, they go logarithmically with the energy scale. So once you understand this, and the fact that of well, are associated to non-renormalizable theory, or said differently, a non-renormalizable theory always has irrelevant operators, then you come up with a new understanding of why in nature we only see renormalizable theories. Or, I mean, at particle colliders, it happens that everything is well described by the standard model of particle physics. This is a renormalizable theory. And the fact that it's renormalizable is not because those renormalizable theories are more fundamental, but it is simply a consequence of the fact that irrelevant operators associated to non-renormalizable theories significant at the energy scale that we probe. So in particular, we expect many non-renormalizable or irrelevant operators to also describe the physics, but the thing is that because they decrease from high energy to low energy scales, they become irrelevant at the energies that we probe at particle colliders. There is another interesting consequence of this behavior, which is related to the mass of scalar fields. So as I said, the mass of scalar fields increase as we go towards lower energy scales. But at some point, if you reach a situation in which the renormalized mass is bigger than the energy scale at which you're probing the theory, then this scalar field cannot be excited anymore because it's too massive. So it cannot be produced. And that means that effectively the massive scalar field decouples from the theory at low energy. And that would explain why we don't see any massive scalar in physics, in particle physics. Now, there is, of course, one exception to this rule, which is the Higgs boson. So the Higgs boson is a massive scalar. And actually, we do not understand why there is exception. And it's basically the root of the electroweak hierarchy problem, which I will comment a bit further now. Okay, so so that was a very quick review of renormalization. So now we can well, try to see what's going on with the standard model of particle physics. We can count the number of free parameters in the standard model. There are 20, 18 of which are marginal couplings. So they run only logarithmically with energy. And there are two relevant couplings. There is, well, the mass of the Higgs boson and the cosmological constant, or vacuum energy. Well, particle physicists, they leave out vacuum energy, but I took the liberty to add it because simply it is relevant for cosmology. Okay, so the fact that there is no irrelevant operator, as I said, is expected from the behavior of quantum field theory under renormalization workflow. So there are 18 marginal couplings. That's fine. And there are 2 relevant couplings. But those 2 actually are a bit problematic conceptually. And the reason is the following. So you can like derive the behavior of the mass well, as a function of the energy scale. And you see that at some low energy scale mu, it differs from its value at the UV scale by a quantity proportional to the UV scale itself. So now there is something that is a bit puzzling, because if I say, well, the standard model, well, is a low energy version of a theory defined, let's say, at 100 TeV or at the grand unification scale, or even at Planck scale or whatever, then this MUV would be quite, could be order of this high. The measured value at mu equal, let's say 100 GeV, is of the order of 100 GeV. So how is it possible that this relation is satisfied? And on this side, a small quantity. So that's kind of the puzzle. Or said differently, we naturally expect the mass of the Higgs boson to be of the order of a scale of the theory. Much higher than 100 GeV. So we can have a very similar reasoning with the cosmological constant itself. The difference between the value of the cosmological constant at some low energy scale mu and of the order which is the cosmological constant divided by 8 pi times g Newton. And again, so this quantity is inferred through cosmic acceleration, or well, yeah, well, the Hubble expansion rate, more precisely. It is ever observed in be of the order, again, of the fundamental energy scale. That's what we would expect. Unless there is large cancellations between this term, which is expected to be huge, and the value of the cosmological constant terms. Well, in fact, what we would need in order to reproduce the observed value of the cosmological constant is a cancellation between those 2 terms up to the 120th decimal. So we need cancellation, yeah, at a very high precision. And that's what is called fine-tuning. So this tuning between those 2 terms, then there is something that we don't understand about physics. So perhaps a different way to look at the problem is the following. You have a measurement on cosmological scale cosmological constant. It's of the order of 10 to the minus 12 GeV. You can say, well, let's run backward the renormalization group, the renormalization flow. So let's flow to some higher energy scale mu2. There very quickly along the flow, the value of the cosmological constant will be of the order of the higher energy scale. And if you make a slight perturbation of the value at this higher energy scale and run again the RG flow towards low energy scales, well, you very naturally get a value that is of the order of to connect back to what I just said. So let's imagine that this mu2 is the Planck scale. Then if I make a perturbation at the, well, 120th decimal of the value of the cosmological constant, the fundamental cosmological constant, and run the renormalization group flow, then I would get something order the Planck mass, even at low energies. And this is, of course, not the case. I mean, at least according to standard cosmology. Okay, so this I said. So either one has to accept so large cancellations in the fundamental theory. But this kind of invalidates the way we have done physics so far, which is that, well, usually we rely on the assumption of decoupling between low and high energy scales. And we say that whatever the ultimate theory of physics is, the details, I mean, the fine details of that theory should not matter too much for the purpose of doing low energy physics. But in this case, we have a problem with this assumption of decoupling between low and high energy. Perhaps what I would like to do is perhaps to try to reflect back on last week talk by Eric Curiel, which I very much enjoyed, by the way. So Eric presented what he called principal models, which are, well, models like ideal models, which would satisfy a list of physical properties, but unfortunately, nobody knows about a concrete realization of those principal models. So a fully, a theory described by a bunch of equations, and we could explicitly check that it satisfies all the that we would want. Here, we face kind of a principal model because the whole cosmological constant fine-tuning problem revolves around the relation between low energy effective field theory, which we know very, and some UV theory of which we know nothing, and that I would call the principal model. So yeah, it's very difficult to say, well, fine-tuning doesn't make sense at all if we don't know what the UV theory is. It may happen that there is actually, or that the fundamental theory is such that you have these large cancellations that yield a very small cosmological constant at low energies, but we don't know anything about it, so we're still very uncomfortable with the idea that this can happen. Okay, so that was just a parenthesis. Well, to my own work. So what did we do with together with my collaborators? We simply emphasized that actually the vacuum energy has never been directly observed, and only the Hubble expansion rate of the universe has been observed. Of course, within standard cosmology, in particular the lambda CDM model of cosmology, there is a relation, a direct relation between Hubble expansion rate at late times, when the universe becomes essentially empty, so matter is very much dilute. The relation is simply that the square of the Hubble expansion rate is but is the lambda CDM model of cosmology the end of the story? Is general relativity even the end of the story? Well, many people think it's not the case. Actually, many people view general relativity as an effective field theory that that describes gravity at low energies. So we can ask the question whether this relation between Hubble expansion rate and cosmological constant holds beyond general relativity and the lambda CDM model of cosmology. In particular, what we showed is that it's possible to have a modified theory of gravity the cosmological constant is very large, as expected from the QFT arguments I just gave. But at the same time, it produces a very slow Hubble expansion rate at late times. So the model is the following. It's a scalar tensor theory of gravity. Stein-Hilbert action. But in addition to that, there is a scalar field, phi. So there is a kinetic term for it. It is massive, it has self-interaction, but it has also couplings to the curvature itself. And what we need, I mean, the only requirement we need for this theory to produce the kind of behavior I was describing or was mentioning are the following. We need this non-minimal coupling psi to curvature to be negative. And the reason for this is that we want the scalar field to be initially unstable and to grow, and to develop a negative energy density that will and perhaps length vacuum. We need those. We also need those quartic couplings lambda and lambda r to be positive, and this is for the potential to be bounded from below and for the scalar to eventually stabilize. And finally, we need a hierarchy between couplings. So we need the mass in Planck units and those two marginal couplings to be much smaller than the absolute value of psi. And the reason is that we want this unstable regime to last long enough and to give a chance to the scalar field to produce a large amount of negative energy density. So if these criterion are satisfied, then we have attractor solutions, cosmological attractor solutions. So whatever initial condition system are, eventually they're all attracted towards constant expansion, so Hubble expansion rate being constant. And what we want is that the final Hubble expansion rate, as measured in Planck units, be the observed one. But in particular, it should be 10 to the minus 120. So that's the goal of the model. So the way it works is basically the following. So here I'm showing the potential for the scalar field. So there are many terms that contribute to it. There is this constant piece, which is the large and perhaps initially the scalar field will probably sit on top of the potential, but it will roll down either side of the hat. And as it rolls down, well, the energy density, the total energy density decreases. Now, so if the total energy density decreases, that has an effect on the cosmological background through Friedman's equation. And as you know, Friedman equation is just the statement that the curvature is proportional to the energy density. So as the energy density decreases, the curvature also decreases, decelerates. But this has an effect on the potential itself due to the non-minimal complex. So due to the presence of those non-minimal, well, along the evolution of the system, the potential itself will flatten out. And eventually the scalar field will settle down to a dynamically selected minimum. And this dynamically selected minimum is such that there is a very small residual energy density, which would account for the late time Hubble expansion rate that we measure today. So here is a numerical well, is the attractor value. And as you can see, initially it's small, but it grows exponentially towards this attractor value and settles down to it. On the right panel, you see the Hubble expansion rate. And initially, it's very large because constant phase of Hubble expansion with much slower expansion rate, much lower expansion. So notice that very simple model. It's not realistic in the sense that it describes only an empty universe. So there is only vacuum energy taken into account in the model. And it simply describes a modified theory of gravity where we have this additional non-minimally coupled scalar. So in the last paper that pushed towards something more realistic, and in particular, what happens to this scenario when you add matter into the game, and that's what we did. So for simplicity, let me just in the Lagrangian, so the mass and the quartic coupling of the scalar field to 0. And we're going to assume that the attractor solution in the universe, and see, well, from there on, what's going, I mean, what happens. So so we add matter to the system, and we ask whether explain how it works. Well, I have to show you a couple of. Since it's a scalar tensor theory of gravity, the measured gravitational strength in the Lagrange. The reason, let me go back to this. The reason is that there are, well, there's this term, which is the usual curvature term in the Einstein-Hilbert action, but there are other terms proportional to curvature. For a static configuration of the scalar field, well, it's very easy to realize that the Barrow-Newton constant receives correction from those two terms in the Lagrangian. And that means constant is much lower than the Barrow-Newton constant. So perhaps that could help understand why gravity is so weak, although that's not what we're going to focus on right now. And this is described by Friedmann equation. So here, the usual Friedmann equation that we encountered is a bit different, because there is usually not this term associated to the non-minimally coupled scalar field. And there is usually a cosmological constant term, but a very small one to account for the slow Hubble expansion. But here, in this case, this is big, because that was our assumption. We don't want to cosmological constant. Itself of the scalar field, well, grows with h, so it grows with curvature. That means that I can put this term on the left-hand side of the equation, and I can rewrite Friedmann equation in this way, where you see that now there is no well, explicit phi term. This has been somehow reabsorbed. And the effect of this reabsorption is simply to replace G by the effective Newton constant that is actually measured by experiment, and to replace the large cosmological constant by a different constant related origin by this relation. Now we can play with the value of the parameters in the Lagrangian in order for this to be as small as we want. In particular, we know that we need, for consistency with observations, we know that we need this to be of order 10 to the minus 120. And we can achieve this by setting lambda r to, or by, I mean, we can say that this v10 to the minus 60, if we say, for example, that psi is of order 1. So that's basically, well, how the model goes. So yeah, I should give like the of all of this. The conclusion is that if we assume that the attractor solution was already reached prior to matter and radiation domination, then standard cosmology goes through. We could the standard Friedman equation. And the gain is that we allow for a very large vacuum energy at the cost of in the Lagrange. So in our last paper, we've also done a bit more. We looked at non-zero values of these couplings. We've studied the stability of the model under robust under dynamical perturbations, and in fact it is. And we also checked constraints on, well, coming from solar system tests degree of freedom in the game. The gravitational field of massive bodies such as the sun may be different from the usual Schwarzschild solution. So there is a way to parameterize the gravitational field of a massive body. It's called post-Newtonian parameterization. And it happens that our model, in our model, the value of the important parameter gamma is equal to 1 as in general relativity. So the model is perfectly compatible with well, known constraints on gravity at the solar system scale. So that's the conclusion for this model. Now you could say, well, that's great, but you could say that we've simply exchanged a small value for the cosmological constant for, well, also very small value for some other parameter. So how does this resolve the fine-tuning problem? And the reason is that having small values for those other coupling constants is not a problem from the point of view of QFT. So you can very easily, I mean, a simple way to check that a small value makes sense in QFT is to compute radiative corrections to it. In this case, I can compute, for example, the radiative correction to the mass of the Gilman diagram. And although it's proportional to the UV scale, so if the UV scale is the Planck scale, then this may be dangerous, but it's also suppressed by the one of the small parameters in the model. In this case, the quartic coupling. Similarly, so I said that I need a quartic coupling, a very small quartic coupling. I can compute its radiative correction. And as you can see, well, first of all, since it's marginal, it only depends logarithmically on the UV scale, but it's also suppressed by powers of the small parameters themselves. So in particular, if you say, well, for consistency, I need radiative correction to the mass smaller than the tree-level value of the mass itself, then this puts a constraint on some of the parameters of the model. So in particular, you have this combination of fundamental parameters. For complete naturalness, you could say, well, this should be of order 1. So that would mean that the fundamental theory of gravity would be would have the Planck scale as a fundamental cutoff. So this would be of order 1, and you need 1 to be much smaller than this combination, but by taking arbitrarily small lambda, you can easily satisfy this condition. Okay, so well, that's basically all I had to say. So I first, well, try to review for you the cosmological constant problem, and then I presented a scenario, a cosmological scenario in which we can accommodate for a large cosmological constant value, but at the same time produce cosmology that that is consistent with observations, at least starting from radiation domination. So it's, I mean, at the very coarse grain level that we have worked at, it's essentially indistinguishable from general relativity on both scales. But there's, of course, I mean, to really claim that it's a convincing realistic model, well, there are many more many more checks to be made and to compare to all the data we have about our universe. But of course, this goes much beyond well, what we have actually done. And perhaps one loose end is what happens before radiation. So we know that there should be an inflationary phase. However, the problem is that we don't really know what inflation is. So we don't know what is the dynamics of, yeah, what is the underlying dynamics of inflation. So it's very difficult at the moment to say how our model could also accommodate for that. Okay, well, thanks a lot. And if there are any questions, I will be happy to answer them.
So let's thank Kevin for a wonderful, wonderful talk. We can start questions straight away. So please, if you have any questions, either raise your hand or just come in.
I have a question, Kevin. So thank you for a very nice and beautifully presented talk. My question is, I'm not so worried about how realistic the model is or whether it includes, you know, taking into account what this Higgs field would mean for inflation or generalization. My question really is from the couplings.
Right.
Because it seems to me that the heart of this principled model is that it's a worthwhile trade to trade. I mean, it seems to me your contention is trading the naturalness problem as it exists now for a hierarchy of couplings is a worthwhile exchange. That seems to me if I had to summarize in one sentence what the point of this talk is.
Yeah, right, exactly. Yeah, you're right. Totally
so
right.
my question is, when you introduce a softly broken symmetry there, the idea would somehow be that symmetry breaking is itself, in some definition of naturalness, more natural than tuning to 34 or 120 decimal points.
Yeah, that's, I mean, that's a calculated, statement that having something like this where, well, a configuration of couplings that would be small, but that would be protected in some sense against radiative corrections, that's considered closer to naturalness, in the sense that you now only need to explain what is the, well, underlying symmetry breaking pattern that would protect those couplings.
So what kind of ratios of couplings would you get in the toy model, in the principled model? How
right, so
are they?
Here, one in Planck units. And then there's a kind of freedom because there are so many parameters, but you could say, well, let's fix psi to -1. We can actually let m and lambda to be 0 if we want. They need to be very small, but the precise value does not matter too much. The really crucial guy is this one, lambda r. If you set 10 to the -60. But this 10 to the, although it's arguably s constant here to be 10 to the -120, they're on very different footing, well, with respect to
Thank you.
You're welcome.
Could I ask something?
Of course.
Sure.
Well, thanks. That was a beautiful talk. It was very clear. But all this kind of work, this view of the cosmological constant, which sort of predicates it on an anti-Einsteinian idea, in that I think Einstein regarded the cosmological term in the Einstein field equations as part of the geometry. But since the 1980s or something, we sort of moved it to the right-hand side and regard the lambda g mu term as part of the energy momentum tensor, hence its interpretation as a dark energy subject to the formalism of quantum field theory. But is it possible to, in view of the sort of problems you discuss, perhaps have solved, but there are still problems, doesn't it make more sense to go back to Einstein's view and regard the cosmological having nothing to do with quantum field theory? Does this make any sense to you, this question?
I would say there is a flow in this view, because you could of course say that, well, lambda could be, okay, well, you could say why not? And lambda would just be some classical parameter. But there would be the issue that quantum fields themselves, they generate vacuum energy that satisfies all the properties of the cosmological constant. So in some sense, you could have two terms. You could have a classical one, which would be this one, but for another term that would look exactly like it, but which would have a quantum origin.
But if that's your point of view, you're basically starting doing quantum field theory in curved space-time in a regime where it seems to idea of quantum field theory in curved space-time, which is a strange semi-classical idea. This is also controversial in Hawking radiation, where you apply it in a regime where it simply doesn't apply. Does that make sense?
I'm not sure why it would not apply.
Bizarre mixture of classical GR and I would say, but this is of the evaporation of.
I would argue that the situation is very different compared to black hole evaporation, because black hole evaporation, yeah, it's true that there is a moment at the end of the evaporation is very Planckian. Logical scale. So it's the other, it's the infrared spectrum. So you would argue that QFT in curved space-time should make sense on cosmological scales at late times. And don't we see then much larger? But I mean, there is no yeah. It's always possible to argue that sure, QFT.
No.